going to be talking about the unknown universe, but let me first start by us here on Earth. Now, we are accustomed to thinking these days that we are very small in the context of the universe, and that the Earth is simply a speck of dust in the universe. And our sun, the star that sustains life on Earth, is but one of the myriad of stars in the universe. And that our sun is one of the 100 billion stars in a galaxy called the Milky Way. And that our Milky Way is only one of zillions of galaxies in the universe. And if you think that is a very clouded picture, just imagine that this picture is the size of a 1 cent coin if you hold it up in the sky. So you can imagine how large our universe is. But before I go on to the next part of my talk, let us go back to the beginning. Because in the beginning, as you know, there was the Big Bang, when the universe came into existence about 15 billion years ago, plus or minus 2 billion years. And this is going to be a little bit overpowering for you, but let me bring you through it. Now, in the beginning, there was time, which was 0. Now, remember that at time equals 0, when the universe was created, or when the universe came into existence, there was no time, no space, and no matter. And time, space, and matter were created with the universe. So it's no point talking about what existed before time equals 0 during the Big Bang, because there was no time. Remember, there's no time, no space, no matter. And everything was created during the Big Bang. And at a split, I wouldn't even say split, 10 to the minus 43 seconds after the universe came into existence, we can see that the universe was very, very small and dense. And what is 10 to the minus 43 to some of these people here? A tenth of a second is 0.1. Now, 10 to the minus 43 is 0. Then you count 43 zeros before you add the 1. That's how short it is. And at the time of 10 to the minus 23 seconds, then we'll see that the universe is starting to expand. It quickly inflates, and then the particles started to form. And it's only 10 to the microsecond that you'll see electrons and protons getting into existence. And way before the 3 minutes of the universe is up, then you'll see the atoms of hydrogen and helium being formed. And you'll see that only when the temperature cools to 10,000 degrees that you start having real hydrogen atoms and helium atoms. Before this, they were ions. They didn't have the electrons going around the protons yet. And things started really happening only 1 billion years after the initial Big Bang. And the galaxies started to be formed only 15 billion years later. Now, all this while, you see that the universe is expanding because there was a Big Bang. Now, the important thing for us to realize then that at the time when the galaxies and stars are formed, the stars were able to create new elements. Now, there are exciting stories here which I won't tell today about how that carbon atom in your body today was created in the belly of a star a distant time ago and a distant place. And so we know now that the universe is made up of galaxies. The galaxies are what we call the building blocks of the universe. And we were very, very, very happy about that at that stage. We did a lot of research on galaxy formation, on galaxy distribution, which also gave us an idea about the structure of the universe. Everything was hunky-dory, except that somebody discovered dark matter. How did we discover dark matter? Now, here's another picture of the universe where we have a cluster of galaxies. Now, when we have individual stars, usually cluster together, which we call, as you would expect, cluster of galaxies. Now, a cluster includes galaxies and any material in the space between the galaxies. The force or glue that holds the cluster together is gravity. This gravity is, as you know, the mutual attraction of everything in the universe for everything else. The space between galaxies in clusters is filled with a hot gas. In fact, in some cases, the gas is so hot, tens of millions of degrees, that it shines in X-rays instead of visible light. By studying the distribution and temperature of the hot gas, we can measure how much of it is being squeezed by the force of gravity from all the material in that particular cluster. Now, this then allows scientists to determine how much total matter or material there is in that part of space. Now, remarkably, it turns out that from the gravitational force deduced from the calculations, there is 5 times more material in clusters of galaxies than we would expect from the galaxies and hot gas that we can see. Indeed, most of the stuff in clusters of galaxies is invisible. So when you look at that picture there, you do not see this dark matter, which is in fact invisible. This invisible stuff is called dark matter, a term coined by scientists called Fritz Zwicky, because he discovered evidence for missing mass in galaxies. Now, this dark matter makes up about 90% of matter in the universe. So despite all the telescopes that are trained on the universe, whether it's in X-rays, infrared, gamma rays, we still don't know, or didn't know, still don't, about 90% of the matter in the universe. Now, this was really disheartening for the scientists. And so what is dark matter? Now, I can see that in this book, it says a little bit about what dark matter is, and maybe I might read this to you. We are much more certain what dark matter is not, more than we know what it is. For instance, we know that it is not in the form of dark clouds or normal matter. That is matter called baryons. Most of you are not physicists, but I have to inform you that there are particles called baryons. We know this because we would be able to detect baryonic clouds by the absorption of the radiation passing through them. Now, secondly, we know that dark matter is not antimatter. Why? Because we do not see the unique gamma rays that are produced when antimatter annihilates with matter. Finally, we can also rule out large galaxy-sized black holes. Of course, we expect that you cannot see black holes, so there must be lots of them, but we cannot right now deduce that they are large galaxy-sized black holes because high concentrations of matter, as they exist in black holes, they bend light as the light passes near them. And we do not see enough of this light bending to suggest that there are enough of such objects to make up the required amount of dark matter that is in existence. However, there are still a few dark matter possibilities that are at this stage viable. So there could still be baryonic matter that could make up the dark matter if it were tied up in brown dwarfs or in small, dense chunks of heavy elements. These possibilities are known as massive astrophysical compact halo objects. So for you guys there, you know, this is a macho thing to be doing. And astronomers, you'll see later, love this kind of acronyms. But the most common view is that dark matter is not baryonic at all, but it is made up of other kinds of exotic particles, and I know guys love exotic particles too, like axions, neutrinos, and we call them WIMPs, weakly interacting massive particles. Now, a possible exotic particle could be the Higgs boson. You know, there's a lot of talk about Higgs boson, or the God particle, as some people choose to call it. Now, the Higgs boson, as you know, explains why particles have mass, and therefore it might explain why the universe has more mass than what we see of the visible universe. So let's go back again to this unknown universe. With all this dark matter that you have, and the visible matter that you see through the Hubble telescope, Chandrasekhar telescope and all that, the astronomers, by the end of the 20th century, late 1990s, were pretty confident with all this mass that there is enough mass to slow down the expansion of the universe. Remember I showed you with the Big Bang, the universe was expanding. Now, two groups competed to determine the difference between the speed of the current expansion and the speed of the expansion in the past. The first group was led by Saul Perlmutter of the Lawrence Berkeley Lab in California. I know I'm not pronouncing this name right, but I don't have an American accent, so I can't do it. And the second group was led by Brian Schmidt, who's also an American, but working in the Mount Stromlo Observatory in Australia. And in his group, there was also Adam Rees, who was from the Johns Hopkins University and who later on joined the Space Telescope Institute. That's the institute that determines who gets to use the Hubble Space Telescope. And these were the three people who won the Nobel Prize in Physics for 2011. And I'm sure you know that too. And so there was friendly competition amongst the two teams. Now, in order to find out whether the universe was accelerating still or not, or slowing, they used what we call type 1 supernovae. And that they used those things as a standard candle or light to measure the distance to decipher the solution to this problem. Now, I need to tell you a little bit about what a type 1a supernova is and why it's important, because this is the basis on which the Nobel Prize was won. So there are two kinds of supernova. One is the one star that is so massive it explodes. There's another star that actually is not big enough to explode, but does. Why? Because they come from what we call binary stars. And a majority of the stars that you see in the universe are actually binary stars. These are stars that have a partner that goes around them. We call them binary stars. Now, one of them, which will be more massive than the other, will undergo the usual stellar evolution. And in the stellar evolution, at some stage, the star will become a giant star. And as that one star, let me call it the primary star, becomes a red giant, its atmosphere will expand, and it will in fact envelop the other star, the secondary star, to a point where the secondary star becomes closer and closer to the primary star. Now, in the meantime, the primary star continues to expand and become a white dwarf. Now, notice that it is not exploding, it's just calmly becoming a white dwarf because it doesn't have enough mass to become a supernova. And our sun actually does not have enough mass to become a supernova. If somebody tells you the sun will be exploding in so many billions of years, they're not telling the truth because it doesn't have enough mass. Now, as the story goes, it's like this. So one star becomes the white dwarf. Now the secondary star also undergoes stellar evolution, and it too will become a red giant. And when it does, its atmosphere will expand, and this atmosphere will be attracted to the white dwarf. Now, this white dwarf now will gather or will acquire more mass. And as it acquires more mass, it then becomes heavy enough, massive enough to explode. Now, the important thing to remember is that this can only happen when the mass of the star reaches 1.4 solar masses. And so, because it must always explode when it reaches 1.4 solar masses, all type 1 supernovae will show the same characteristics. It will blow up and become bright and then die down in the same manner. So if you can look for these stars, wherever they are, you can actually know a lot about where they are because of this very unique but consistent characteristic. On top of that, the astronomers also have to measure the redshift because that will provide the speed at which the star itself is moving within the galaxy itself. Now, what is the redshift? It's like the Doppler shift. And what's the Doppler shift is when the train comes towards you, it has a certain sound. When it pulls the siren, it has a certain sound, and then when it goes away from you, it recedes, it has a certain sound. That is the Doppler shift. And stars show the same type of phenomenon, but we call it the redshift. Now, before you think, okay, they're going to do this, they're going to measure the brightness, get the distance, and then they measure the redshift and get the speed at which they are accelerating, please remember that chasing supernovae challenges not only the limits of science and technology, but also those of logistics. So this is why the people win this Nobel Prize. First, the right kind of supernova has to be found. Second, its redshift and brightness has to be measured. The light curve has to be analyzed over time in order to be able to compare it to other supernovae of the same type at known distances. This required a network of scientists that could decide quickly whether a particular star was a worthy candidate for observations. They needed to be able to switch between telescopes of the different observatories on Earth and have observation time at a telescope which is granted without delay. Now, granting telescope time usually takes months, if not years, and they must have an understanding that once they have a perfect candidate, those observatories must give them the observing time. They needed to act fast because the supernova fades quickly, and at times the two competing research teams that I told you about, they discreetly cross each other's paths. And I have it on some authority that in some cases competition actually turned into cooperation, which is a good thing. Now, the potential pitfalls were numerous, and the scientists were actually reassured by the fact that both teams had reached the same results. All in all, they found some 50 distant supernovae whose light were weaker than expected. But in fact, I'm already giving because there is a surprise, and I'm giving it away to you. And what is that surprise? Now, if cosmic expansion loses speed, which is what the astronomers were expecting, the supernovae should actually appear brighter. Instead, they found some 50 distant supernovae whose light seemed weaker than expected. So what does this mean? It means that the supernovae were fading as they were carried faster and faster away. And in fact, the expansion of the universe is not slowing down. It is in fact accelerating. Now this caused a lot of strife for the astronomers, and they checked and rechecked their work, and they had everybody come together to make sure that they were right. And so what is it that is speeding up the expansion of the universe? For want of a better name, they called it dark energy. Because they had dark matter, so this has to be dark energy. And this term was coined by Michael Turner, who himself won a Nobel Prize for discovering gravitational waves earlier on. And he coined this term, dark energy. What is dark energy? This is the reason why they won the Nobel Prize. Now, again, your book will also tell you the same sort of thing that I'm going to say. One explanation for dark energy, that it is a property of space. Now, Albert Einstein was the first person to realize that empty space is not nothing. Space has amazing properties, many of which we are just beginning to understand. The first property that Einstein discovered is that it is possible for more space to come into existence. One version of Einstein's gravity theory, the version that contains the cosmological constant, for those of you who are familiar with this, makes a prediction that empty space can possess its own energy. And because this energy is a property of space itself, it will not be diluted as space expands. As more space comes into existence, more of this energy would then appear. As a result, this form of energy would cause the universe to expand faster and faster. Unfortunately, no one understands why the cosmological constant is even there, much less why it would have exactly the right value to cause the observed acceleration of the universe. Another explanation for how space requires energy comes from the quantum theory of matter. In this theory, empty space, again we're talking about space here, is actually full of temporary virtual particles. You know, even as a physicist, I find this very hard to comprehend. And that particles are continually formed and then disappear as a result of being in the quantum world. But when physicists try to calculate how much of this energy, of this virtual energy, would give to empty space, right now we're coming up with the wrong answer. Very, very wrong answer. So we don't know whether or not the fact that the virtual particles are there answers the issue of dark energy. Another explanation for dark energy is that it is a new kind of dynamical energy fluid or field, something that fills all of space, but something whose effect on the expansion of the universe is the opposite of matter and normal energy. So the effect of matter, because it has gravity, is to try and contract the universe, but somehow this fluid makes the universe expand and expand even faster. Some theorists have named this quintessence after the fifth element of the Greek philosopher. But if quintessence is the answer, we still don't know what it is like, what it interacts, or why it even exists. Yet another possibility is that Einstein's theory of gravity is wrong. That would not only affect the expansion of the universe, if this theory is wrong, but it would also affect the way that normal matter in galaxies and clusters behave. Anyway, a way of deciding if the solution to the dark energy problem is a new gravitational theory. Remember, we had the Newtonian gravitational theory, then we had the Einstein theory of gravity. And the only way we can know whether we need another new theory is to observe how galaxies come together in a cluster. But if it does turn out that a new theory of gravity is needed, what kind of theory would it be? Whatever it is, though, it must correctly describe the motion of the bodies in the solar system, as Einstein's theory is known to do. Remember that Einstein's theory explained that as well as the Newtonian theory. And it should also give predictions for other aspects of the expanding universe. There are candidate theories, but again, none are compelling, and so the mystery continues. The thing that we need to do is to decide between these various theories is to have more data, better data. And so what is the conclusion of the work of the 3 Nobel laureates? Is that the universe is made up of 72.8% dark energy, 22.6% dark matter, and 4.6% ordinary matter. So all of that universe, the beautiful universe that you see in the astronomy books, through Hubble Space Telescope, through Chandrasekhar Telescope, through the Weber Telescope, whatever, they make up only 5% of the known universe, of the unknown universe. And we get this data by, of course, combining the supernova survey data together with the results of the cosmic microwave background. So it's a little bit more complicated than what I'm telling you and how you get this number, but that is the latest number that they get. And dark energy uniformly fills the entire empty space in the universe. Now, what does this mean to us in terms of an everyday experience? Of course, dark energy does not exert itself locally where we are concerned. It only exerts itself in the large universe. But just think of this analogy. If you throw a ball up, you would expect the ball to come back down under the pull of gravity. But in this case, if dark energy exerts itself, this ball will go higher towards the sky, and not only higher, but faster and faster. So maybe this is the answer to how we're going to launch rockets and launch the next Angkasawan. Huh? So what do we know now? We know that we had the Big Bang. I showed you the Big Bang in the beginning. And we know that there was enough matter to effect some kind of deceleration. So the acceleration decreases. But about 5 billion years ago, when the universe began about, it's there 14, but anyway, between 14 to 16 billion years, the acceleration started to increase. And the theory is that dark energy was there all the time, and so was gravity. But as the gravitational, as the effect of gravity decreases, the effect of dark energy increases and it overtakes gravity, and that's when the acceleration begins again. And so today, we see a tug of war between gravity, which wants to pull everything back together, and dark energy that wants to everything to fly apart. So what will we perceive when we look at the universe that is accelerating? Because of the accelerating expansion, it is projected that most galaxies will eventually cross a type of cosmological event horizon. Now, at this event horizon, don't worry about the words, but what does it mean? that light that is emitted past this event horizon will never be able to reach us at any time in the infinite future. So assuming that dark energy is constant, as we saw in the cosmological constant, the current distance to this cosmological event horizon is about 16 billion light years, meaning that a signal from an event happening at present, if it happens right now, it would eventually be able to reach us in the future if the event was less than 16 billion light years away. But the signal would never reach us if the event was more than 16 billion light years away. Now, as galaxies approach this crossing of the cosmological event horizon, as they call it, the light from these galaxies will become more and more redshifted. Remember, we talked about the redshift, to the point where the signal or where the light becomes, the wavelength becomes too large for us to detect. And the galaxies, although they're there, they will appear to disappear completely. So you see a disappearing universe. That is rather disconcerting, isn't it? And so, as a result of all this universe accelerating, the expansion accelerating, what will happen to the universe? Now, there are several theories. There are several speculative ideas about the future of the universe. One suggests that there is the expansion where the effective force of the dark energy continues growing until it dominates all other forces in the universe. Under this scenario, dark energy will ultimately tear apart all gravitationally bound structures, including galaxies, solar systems, and eventually overcome the electrical and nuclear forces, and they will tear apart even the atoms. And which is why the astronomers call it the Big Rip. Astronomers love to use words like this. On the other hand, another speculative theory is that dark energy might dissipate with time or even become attractive. Because we're only looking at it at this point in time, and it should still do that. Now, such uncertainties leave open the possibility that gravity might yet again rule the day and lead to a universe that contracts onto itself in a big crunch. Now, for some of you who are familiar with this big crunch theory, we know that there is also speculation that from the big crunch, the whole universe will then implode onto itself to this singularity that we saw at the beginning of the Big Bang. And it is likely that the universe will then undergo another Big Bang. And so we'll have a crunch, a bang, a crunch, a bang, and they call it a cyclic model of the universe. But please be aware that even though after the universe collapses and another Big Bang occurs, the matter there will not necessarily be the same as the matter that you and I have here. So we are thinking of being recycled in the next cycle of the Big Bang. You might not be recycled. It could be something totally different. Now, it is also possible that the universe may never have an ending and will continue to in its present state forever. In other words, the universe would continue growing larger with countless generations of stars fading and dimming out. It should then end in a vast, dark, and cold state. But we will still have some structure of the galaxies. And because of this, we call it the Big Chill. So for those young people there who like to chill out, well, this is the ultimate Big Chill. Now, for all intents and purposes then, the universe remains largely unknown. But as a result of our science, our scientific research, some things of this sort of unknown universe we now know. We know that dark energy is everywhere, and its effects increase as space expands. In contrast, gravity's force is stronger when things are close together, and their gravitational force is weaker when they are far apart. Because gravity is weakening with the expansion of space, dark energy now makes up over 2/3 of the energy in the universe. Now, it sounds rather strange that we have no firm idea what makes up 73% of the universe. It's as though we had explored all the land on this planet and never in all our travels encountered an ocean. But now that we've caught sight of one little wave, we want to know more about what this huge, strange, powerful entity really is. So the strangeness of dark energy is thrilling, I hope, to you, and exciting. It shows scientists that there is a gap in our knowledge that needs to be filled, beckoning the way toward an unexplored realm of physics. I saw a few physicists here. We have before us the evidence that the cosmos may be configured vastly different than what we have ever imagined. It would be arrogant for us to believe that all of science is within the human mental grasp, and that there are no more enigmas that will remain to challenge the future generations. Dark energy signifies that we still have a great deal to learn, and shows us that we stand poised for another great leap in our understanding of the universe. Now, in a way of conclusion, I'd like to do two things. I'd like to share this poem with you. Now, after this somewhat philosophical discourse, I'd like to believe that we should be able to see a world in a grain of sand and behold heaven in a wildflower. Imagine that we can hold infinity in the palm of our hand and feel and see eternity in an hour. And then that's the poem by William Blake. Can you have the lights up again, please? As a conclusion, I also like to express my thanks. My thanks to the Academy of Sciences of Malaysia for inviting me to give this talk, the National Space Agency of Malaysia, Angkasa, for hosting this talk. And last but not least, I would like to thank my two children, Adi and Elida, who are the beacons of my life and who patiently and painstakingly prepared this presentation. To them, I'd like to read a surprise poem. I couldn't get them to type it in, so it has to be, I just have to recite it. But this poem by Yeats, I would also like to dedicate to the youth of Malaysia, to whom I have given 20 years of my life, making the dreams of a national space program come true. Had I the heavens embroidered cloths, enwrought with gold and silver light, the blue and the dim and the dark cloths of night, light and half-light, I would spread the cloths under your feet. But I, being poor, have only my dreams. I have spread my dreams under your feet. Tread softly, for you tread on my dreams. Thank you everyone for being such a